Now I have the pleasure to introduce Geoffrey, our last speaker, but not the least, of course. Let me say a few words. Most of you know him in any case. Geoffrey is a theoretical physicist by training. His primary interests have been in fundamental questions in physics, especially those concerning the elementary particles, their interactions, and cosmological implications. Geoffrey has been president of the Santa Fe Institute. He was the leader of the high energy physics group at Los Alamos and recently published his new bestseller, Scale. Please take the stage.
Nice to be here. Well, let's see. Yeah, you mentioned my book, which put me in an awkward position because I think I must have misunderstood the directions because it was said you shouldn't talk about things that you're working on and the public and all the rest. And that seems to have been violated, if that were true, throughout much of this day. And so I thought I can't talk about anything that's written in my book, in which case the talk is finished. Because I addressed the questions that you brought up. So what I did is I started thinking about, instead of, what is complexity, well, although I will talk about that a little bit, about some of these questions of the history of dealing with complex systems and so on, and some of the more recent work, I thought I would talk about four things that occurred to me. One might be of interest for future directions, some of which already exist, and some of which have been touched upon either implicitly or explicitly by many of the speakers today. The first is, I'm going to miss out my list, the first is to do with big data, AI, machine learning, etc. And the question is, it seems to me for those of us that consider ourselves dealing with complex systems and have a transdisciplinary view of things and maybe a bigger picture view, is to address this question, a sort of philosophical, philosophy of science question, is this in fact a paradigm shift? Is it what some people have called the fourth paradigm? The other three paradigms, may I remind you, are just observation, originally observation, then development of theory and model and mechanism, the very stuff of many of us think of as science, and certainly of the physical sciences, and then the development, third paradigm is often considered the coming of computation and therefore of simulation, and that's led to what some people call the fourth paradigm, which is the whole question of just using data itself and potentially algorithmic machine learning to do our science and solve all of these fantastic societal problems. And some of you have addressed this, and some of you use this. So, I'm a tremendous fan of big data and of AI and of machine learning, even though I can't do any of it. But this is what I subscribe to. This says much better than what I think about it. And it was written already a few years ago by the great biologist Sidney Brenner, who says the following: biological research, you might as well put in there complex, anything to do with this we're talking about today, anything to do with complexity, is in crisis. Technology gives us the tools to analyze organisms at all scales, but we are drowning in a sea of data and thirsting for some theoretical framework with which to understand it. Although many believe that more is better, history tells us that least is best. We need theory and a firm grasp of the nature of the objects we study to predict the rest. That's pretty much how I feel. That is, without having a conceptual framework and principles, a quantitative, mathematizable, computable, in some very general sense, predictive framework, I think we're potentially in trouble. So the way I like to think of it, yes, we want big data, AI, and the rest, but it also needs something called big theory, and I think it's incumbent upon us to think about what that might be and the structure of it, and how in any specific problem needs to be put into some sort of context of a traditional big theory. And in particular, mindless big data is probably bad and even dangerous. I say that because in the work that I do that transcends into the corporate and business world, where all this stuff is hyped to some extraordinary degree, in the same way as someone talked about earlier, but in particular in the way, for example, nanotechnology was 20 years ago, was going to completely revolutionize everything. And maybe it eventually will in some way. But it's not the panacea of all things, but importantly, we need some major conceptual framework, because data, and this is in many ways, is not neutral and it's not virgin, ever. It never is, because someone has to decide what to measure and what density to measure it is, where to take it, and so on. So that's my first thing, my first point. Second is, which has also been addressed, is the whole conceptual framework of the integration between energy, metabolism, the physicality of the system, the infrastructure of the system, with the flows of information. And I've written something down there. And of course, so some people talked about the brain, consciousness, whatever. So when we normally think about the brain, and we use network theory, the buzzword network theory, we draw these pictures, you see these photographs of neurons and axons and so on. We're thinking of information flow, and we think that that's going to explain the brain. And obviously you need to understand that in a deep way to do it, both the network aspect of it and the physics and the biology of it. But there's something else going on there, and someone did mention it today, and that is that all of that needs to be supported by energy, and that's a completely different network that is integrated with it. And as I'm sure all of you know, when you do MRI studies, fMRI studies, you don't measure this. Well, you know more than you actually, what you're measuring is actually this. And they're very different networks, and they are completely integrated, and they constrain one another. So in order eventually to understand the brain, we need to understand those in unison, and that goes in the same way for, this is the one or two places where I touch upon my own work, this, which is the classic picture of network theory, where there's all kinds of theorems and so on. But I don't care how many theorems you prove and how much data analysis and how much data you have on that, that is not what is happening in the real world. Because what's happening in the real world is when I call Peter, I'm standing here and he's sitting there. Not only that, he's tired and he's hungry and he wants to go back and he's going to walk down there or he's going to take a flight tomorrow. In other words, this is necessarily integrated with this, with the fact that we are sitting on a two-dimensional surface, that in order to communicate, we have to be in the kitchen, in your lab, sitting on the toilet, in a shower, sitting on a bus or a train, moving, because you have to move. You must move because you have to go home, you have to go to work, you have to get groceries and so on. So these are essential parts of networks, and these two networks, again, cannot be treated at a fundamental level independently. They're totally intertwined and have to be integrated. Third, this is my picture. This is a picture, a photograph. Some of you may have seen this, because I know that some people have heard me talk on this. This is a photograph taken the year I was born, 1940, by a satellite of the night lights of the Earth. Obviously not. Couldn't have been, because there weren't any satellites. Very good. It's what I have calculated as to what it would have looked like, had there been one. That's what it would have looked like. in the diddly little short time of my life, this is what it looks like. It's, as you well know, in that short time, it has completely, the earth has started, it's beautiful, but it's frightening. And what does that represent? That simply represents urbanization. That's us, living, building cities and so on. And it's been happening at a faster than exponential rate, this phenomenon. So much so that today, what's today? Thursday. By next Thursday, there will be the equivalent of Finland in terms of infrastructure for urbanization on this planet. And by the following Thursday, another Finland. And on into mid-century. That's the world we live in. And we need, if we're going to deal with the problems that everybody's brought up, we need to recognize that we're living in this faster than exponential, expanding universe, socioeconomic universe. Okay, and there it is. This is obviously another one which many of you have seen. Obviously, you've all seen this. This is, and it's all been stimulated, of course, this is the population growth, and it's all been stimulated by the Industrial Revolution, the discovery of fossil fuels, and the invention and fantastic discovery of entrepreneurship and capitalism. But that leads to all kinds of problems, and one of them is that any growth in socioeconomic terms, in macroeconomic terms, typically has this behavior. You start fast. Someone mentioned it, so I have to say it. You hit a finite time singularity, and you have to start over again by inventing, by making another innovation. And so it is, and so you go on. Otherwise, you collapse, and you have to do this at a faster and faster rate. And there it is. There's not mine. This is not my data. Just the version of the singularities, the various singularities, or avoidance of singularities by innovation. And that's on a log plot, and one can predict the slope of that line. I'm not going to go into it. And here's another version of it. This is time to reach 10 million customers for various much lower level innovations, but you can see it's getting shorter and shorter, and it follows the same rules as the macroscopic one. And what does that lead to? So here's the thing that is so extraordinary. This has led to the following. So this is work I did a long time ago, but it's not, I want to show it for illustration. This is metabolic rate versus mass. Who is the young man that just said this absolutely absurd statement about power laws have, where is he? There he is. You must be out of your mind. That says nothing about a system that is evolved by natural selection. Of course, you need to understand that. And that's the crucial point. You need to understand mechanistically, well, how in the fuck did that happen when you have a naively random process? Okay, we won't come to that. That's been done. But here's the point I want to emphasize. We evolved to conform to this, and we evolved operating at 100 watts. That's what everybody in this room is operating at, sitting here. Our social metabolic rate, what you're really operating at now, through the Industrial Revolution and creating all this stuff and inventing computers and iPhones and all the other rubbish that we have to have, that's where we are. We're up there. We've completely violated by creating an urban environment. So we've gone from 100 watts to 11,000 watts, a factor of 100, which is fantastic. And we need to understand that in much greater detail and the implications of that. And I want to finish with just a couple of quotes. Since I'm in Vienna, so I have to quote the great economist Joseph Schumpeter, who made this famous statement, creative destruction is the essential fact about capitalism. But I find this statement that he made much more to the point than one that is actually implicit in what I've said, but is also part of what we should be thinking about here. All successful people are standing on ground that is crumbling beneath their feet. Or to put it slightly differently, all successful institutions are standing on ground that is crumbling beneath their feet. That's the whole point, and that's who we are as human beings. And the singularity, you don't have to believe anything I say, but this was made by von Neumann in the 50s. The ever-accelerating progress of technology gives the appearance of approaching some essential singularity, in mathematical sense, in the history of the race beyond which human affairs, as we know them, could not continue. And so that's the problem we have to face. I got one more thing, and I can do it very quickly, and this is because you said be provocative, and that is time. Time, understanding time. So most of us were brought up with this sense of time, Newtonian time. And you write T, time, punkt, finished, right? X, space, absolute, etc. This is from Doctor Who. I don't know if many of you know, it doesn't even matter. It's a BBC television thing, very popular in the United Kingdom and in the United States. Here's what they say, here's what he says time is. People assume that time is a strict progression of cause to effect, but actually, from a non-linear, non-subjective, complex adaptive systems viewpoint, it's more like a big ball of wibbly-wobbly, tiny-whiny stuff. Like this, okay? Or this. Slow when you wait, fast when you're late, deadly when you're sad, short when you're happy, endless when you're in pain, long when you're fly, etc. So someone here, several people said, we got to be in touch with the real world and reality. This is about as real as you can get, and in many ways more real than writing T equals time, which I've spent my whole life doing. So here's another one. This is Einstein on the same subject. When you sit with a pretty girl for 2 hours, you think it's only a minute, but when you sit on a hot stove for a minute, you think it's 2 hours. That's relativity. Okay. So time is critical, and it's critical for someone my age, because we need to understand what time did here. And and I am quite obsessed with aging and my own death. And here's what Steve Jobs said about it, which I also completely concur with. No one wants to die. Even people, this is all to do with time, remember. That's why we complexity scientists need to think about time. No one wants to die. Even people who want to go to heaven don't want to die to get there. And yet death is the destination we all share. No one has ever escaped it, and that is how it should be, because death is very likely the single best invention of life. It's life change agent. It clears out the old to make way for the new. That's what Schumpeter was saying, of course. And I will miss this out because I'm late. And finally, I show a picture here of two famous, well, one we may not think of as a scientist, but two famous intellectuals. Some of you better recognize the man on the right. And in fact, everybody ought to recognize the man on the right. And if you don't, you shouldn't be here, in my opinion. That's Wolfgang Pauli. And on the left, okay, you're excused if you don't recognize him. That's Carl Jung, psychologist, and there was a decade-long dialogue between them, and some to do with the nature of time, and Pauli bringing the physics view, and Jung a kind of psychological view. And here's what he said. Both of us, that is, this is what Pauli said, both of us seem to agree that the future of Jung's idea is not with psychotherapy, but with the utilitarian, holistic concept of nature and the position of man in it. Unified theory, unus mundus. And that's what we need to think about for complexity. It's not just solving all these fucking problems. Yes, we need to do that. But if we don't start to think in bigger conceptual terms, going back to what I said at the beginning, I think we're just, and I think you said it in your thing, we just become another piece in the scientific fabric. Now, unus mundus, string theory, or this, finished. Thank you.